In this lecture, we're going to have a look at differentiation. Okay, so differentiation has many applications, and you'll see it quite a lot when we start to have a look at engineering science, for example. You'll see things such as velocity and acceleration written as derivatives. Okay, so what we're actually looking at then in terms of the pure mathematics aspect of it. Well, what we're actually looking at when we're looking at a function here on a set of axes is the gradient of a function. Okay, so the gradient is a rate of change of the coordinates along this function. Okay, so the way I like to introduce this is by first of all looking at a linear function such as this, y equals 2x plus 3. Now what we've probably seen before is this little formula here, y equals mx plus c. Now every linear function is in this form, y equals mx plus c. Now what do these letters stand for? Well, m is what we call the gradient. Okay, so this is the rate of change of the coordinates, or the slope of the function. C is what we call the y-intercept. So this is where it crosses the y-axis, and y and x here then are coordinates along this function. So if we were to look at this function here, for example, then y equals 2x plus 3, we could tell straight away that the gradient, yes, the slope of this function is 2, and the y-intercept where it crosses the y-axis is 3. Okay, and of course this gradient doesn't deviate at all, it doesn't change because of the nature of this function being a linear function. This is a straight line, of course, so I could extrapolate this even further along, and the gradient would be 2 all along this function. And how do we work out what this gradient, what this m value is then? Well, if we were given a straight line, such as this, okay, so say this is a function now somewhere on top of a pair of axes. We've got coordinates, of course, all along this line. So say, for example, we've got these two coordinates here. So we've got the coordinate 1, 2, and the coordinate 4, 7. And always remember, when we're talking about coordinates, they're in this form, yeah, x and y. So how would we find the gradient here? Well, what we've got to do is we've got to find the difference of the y coordinates and the difference of the x coordinates, and we find the ratio between those two. Okay, so we divide them basically. So here, of course, we've got a difference in y coordinate. Okay, so if I just write this in here, we've got a difference in y coordinates. Sometimes you call this delta. Okay, so just a triangle, delta y. And we've also got a change in x coordinate, and we call this delta x. Okay, so to find m then, the gradient, like I said, it's the difference in y coordinates over the difference in x coordinates. Okay, so difference in y over the difference in x. So in this case then, what we got, 7 minus 2 over 4 minus 1. So that gives us a gradient of 5 over 3. Now it doesn't matter which coordinate you take from which, as long as you're consistent. Okay, so I've done 7 minus 2, so I've got to make sure then I do 4 minus 1. Okay, I could of course done it the other way around, 2 minus 7 and 1 minus 4. Yes, so you've just got to be consistent with your subtraction. So what we've actually got here then this delta y over delta x is what we call a derivative. Okay, so you don't tend to write derivatives down like this, delta y, delta x. You tend to use this notation here, dy dx. Okay, dy dx. So this is what we call a first derivative. Okay, this is what we call a first derivative. So the name for this notation is called Leibniz notation. Okay, Leibniz notation. And of course you can get second derivatives, third derivatives, fourth derivatives, and so on. The most important ones really that we will see is first and second derivatives. With the second derivatives, you can find what we call turning points of a function, so where a function starts to turn from one direction to the other, or stationary points. Okay, so this is an example then of a first derivative. An example of a second derivative would be this. So the way we say this is d2y over dx squared. That's the second derivative, and it goes in that pattern then. So we've got d3y over dx cubed. That's the third derivative, and so on. Okay, so this is what we call Leibniz notation. Okay, always nice to know the names for these things. So you'll see Leibniz notation quite a lot, particularly when you're studying physics or engineering science, because we see that things such as velocity and acceleration can be expressed as derivatives in Leibniz notation. Okay, so quite often you see, for example, velocity written down as dx dt, so how distance changes with time, and for acceleration you will also see dv dt. Okay, so this is how velocity changes with time. There's another way of writing that as well as a second derivative. You can also write that down as d2x over dt squared. Okay, so that's another way of writing down this velocity derivative, acceleration derivative. But of course we don't go into the applications of it in this module, but you will see them in various places. Another type of notation that you can see, you don't tend to see too much in engineering, but you do see it particularly in mathematics and physics, is what we call Lagrange notation. Okay, Lagrange notation. And this looks slightly easier actually on the face of it. So for example, a first derivative would be this. Okay, so instead of writing our function down as y equals to something, so say we had that one earlier, 2x plus 3, you can also write this y as f of x, so y is a function of x. So it looks a bit more complicated really, and I suppose it is when you start applying it to engineering, but for maths we do sometimes write down f of x, so function of x, instead of y. Okay, so yeah, if you want to do the first derivative of that function, then we have f dash x, okay, or sometimes they say f prime of x. So that's the first derivative. Second derivative, f double prime or double dash x, and it keeps going in that pattern. Then I think you can get to either 3 or 4, and they start putting numbers in like this then. Okay, but generally, like I said earlier, we tend to only deal with first, second, and sometimes third derivatives. Okay, particularly in engineering science, of course, we're looking at velocity and acceleration, and you don't tend to go beyond that then until you start looking at physics and very small particles. Okay, so, you know, if we start looking at third and fourth and fifth derivatives, we start looking at things like jerk, okay, or jolt, sometimes it's called, and jounce. Like I said, because these are very, very small accelerations and rates of change of accelerations, you tend to only see it in very small particles. So we don't tend to study it at this level, at least. So that's enough about notation. Let's go back to what we're actually doing when we're finding a derivative. Okay, so remember I said what we're doing is we're finding a gradient. So let's write that one down that we had a second ago then. Y equals 2x plus 3. So remember what we said, this term here, what we call m, yeah, in the y equals mx plus c, this is m. We know that the gradient of this function is 2 all along the function because it's a straight line. Okay, so that's fine. Now the problem is when we start looking at something like this. So say we've got this function y equals x squared. Now, the problem is here, of course, if I ask you what is the gradient of this function, you couldn't really answer me, could you? Not with a bit more information. Now, of course, because this function isn't linear, the gradient changes as x changes, doesn't it? Here, for example, the gradient looks like this. Here, the gradient looks like this. And of course, at 0 here, the gradient is a horizontal line here. So how do we find this gradient then? Well, what we have to do is we have to differentiate our function. Okay, now I can tell you quickly that the derivative of x squared is equals to 2x. Okay, and we'll see how I got to that in a second. But the derivative of x squared is 2x. So this is a bit strange, isn't it? Because it's saying that now our gradient has got an x in it. And what does this x mean? Well, this means that anywhere along this function, the gradient is affected by the x coordinate. Yes? So if I asked you, for example, what is the gradient at, say, x equals -2, what we'd have to do is substitute this value of -2 into this gradient. It's almost like a gradient formula. We substitute it into this and we get gradient as -4, 2 times -2. Okay, so we've got m here is -4. If I ask you what's the gradient at, say, x equals +2, sub it into here, of course we get m is equals to 4. And if I said to you, what's the gradient at 0? So x equals 0 in the middle here. Of course, we get 2 times 0, and we have a gradient of 0. Okay, so this is what we call a turning point. So horizontal line, of course, there is no slope. There is no rate of change at that point. So the gradient is 0. And in general, what we have to remember is positive gradients go in this direction. Okay, so it can be anywhere on these axes, but it's going in that direction. Negative gradients in this direction, and horizontal gradients are 0. Okay, m is equals to 0. So how did I get to this 2x then from the x squared? Yeah, the function given to us was x squared. How did I get to this gradient of 2x? Now, what we need to have a look at is a very important, what we call a standard derivative. Okay, so if we've got a function in this form, y equals x to the power n, okay, if we've got this function y equals x to the power n, where n is a number, dy dx, the first derivative, is equals to nx to the n minus 1. Okay, nx to the n minus 1. extremely important. And it doesn't look very nice initially, but all it's asking you to do is bring this power down in front of the x and then take 1 away from the power. Okay, bring the power down in front and take 1 from the power. So that one that I did a second ago, what do we have? Y equals x squared. What did I do? I brought the power down in front. So bring this power down in front, 2x, and of course you take 1 away from the power, so we end up with 2x to the power 1, and of course 2x to the power 1 is just 2x. Okay, so this is how I got to that gradient of 2x. And if you wanted to then find a second derivative or a third derivative, what you would do is keep differentiating your answer. Okay, so we'll have a look at 1 or 2 of those later on. Okay, so let's have a look then at the different types of functions that we can differentiate in that form. Okay, so using that standard derivative. So for example then, if we have a look at this one, 6x cubed minus 2x squared plus 4x. We'll leave it there, I think. So y equals 6x cubed minus 2x plus 4x. Right, so when we've got something like this, what we've got to remember when we want to differentiate something is we want to have separate terms. Okay, so we want to have terms separated by positives or negatives, such as something we've got here. If we've got something multiplied together, what we want to do is we want to either multiply those brackets, if they're brackets, we want to multiply them out so we can get separate terms like this. Or if they don't multiply out and it's a bit more of a complicated function, we've got to use some of what we call the rules of differentiation, okay, namely the product rule and quotient rule and function of a function rule. Okay, and function of function rule, sometimes called chain rule, but we'll have a look at that later on. But here we've got separate terms, so we can differentiate this straight away. Okay, so if we ever see a function like this, it's great because it means we can go straight for it. So bringing the power down in front, now if there's a number in front of the x, they become multiplied. Okay, so there's a long-winded way of doing this, and I'll do it for this first one. But what we're actually doing is we're differentiating this x cubed. Okay, so we've got 6 multiplied by the derivative of x cubed, which is 3x squared. Yes, bring the power down in front, take 1 away from the power, minus, because we've got a minus here, 2 multiplied by, now we're differentiating x squared. So bring the power down in front, take 1 away from the power. Yes, so take 1 away from the power and we just get x plus 4. Now this one's a bit more of a complicated one. When we're differentiating a number times x, what we end up with is always just the number on its own. Okay, and the reason being for that, if we were differentiating y equals 4x, of course this now is x to the power 1, yes, 4x to the power 1. If we differentiate this as normal, so dy dx, bring the power down in front, multiplies by the 4, so we just get 4, take 1 away from the power, and we get x to the 0. And of course anything to the power 0 is equals to 1. So we end up with 4 times 1, which is 4. Okay, which makes sense. You know, if this was on a graph, y equals 4x, it would just have a constant gradient of 4. Yes, it's a linear function. Okay, so that's the reason why you just end up with a number. But all you've got to remember really is if you've got a number times x, you just end up with a number when you differentiate it. Okay, so 10x differentiated is 10, for example, and same with negative numbers and fractions. Okay, so let's multiply this out then. So 6 times 3 is 18, x squared minus 2 times 2 is minus 4x plus the 4 on the end. Okay, so here now we've got our derivative of this function. So I've done it the long-winded way here. The quicker way of saying it would be to say the number comes down in front, and if there's a number there in front already, so if you've got a coefficient there already, that power becomes multiplied by that number. Okay, so 3 comes down in front, multiplies by the 6, gives you the 18. Take 1 off the power. Same here, 2 comes down in front, multiplies by the minus 2. We get minus 4. Take 1 off the power. And of course with this one, remember I just said that if it's a number times x, you just end up with the number in front of the x. So that's the way I would normally differentiate rather than writing this line down. If you're more comfortable doing that, of course, you know, go ahead, but it's a bit of a long-winded way of doing it, especially when you've got a lot of terms in the derivative. Another quick example then of a function that looks something like this. So if we go 5x to the 4 plus 3x squared plus 5. Okay, 5x to the 4 plus 3x squared plus 5. So let's differentiate this. So dy dx is equals to, so bring the power down in front. There's a number already, so they multiply. 4 times 5 is 20x. Take 1 off the power. So we've got x cubed plus 2 comes down in front. There's a 3 there already, so they multiply. 6x to the power 1. Now we have just a number on the end here, so slightly different to earlier when we had an x multiplied by it. Now what we've got to remember is whenever you differentiate a constant, okay, in other words a number, we get 0. Okay, whenever we differentiate a constant, we get 0. And normally, of course, you wouldn't write 0 in there. It's just for this example, I've written it in. And why do we get 0? Well, for example, if I asked you to draw this function, y equals 5, y equals 5 would be a straight line here going through the point y equals 5, as the function suggests. And of course, thinking back to earlier, remember now we're finding slopes, yeah, or gradients, rates of change. Here we haven't got any slope. Therefore, of course, the line, the function, is a horizontal line. Yeah, so we don't have any slope, therefore the gradient is equals to 0. Okay, so dy dx here is equals to 0. So always remember, whenever you have a constant and you have to differentiate it, we get 0. Next function to differentiate then. So we've got y equals 2x plus 3 multiplied by x plus 1. Now, of course, here we've got two terms multiplied together, haven't we? We've got two brackets multiplied together. So the first thing we need to do is try to get separate terms. So what we need to do is multiply this out. And of course, if you've got two terms that don't multiply out, so for example, when we start having a look at trigonometric functions, we've got to use what we call the product rule. Okay, but for this one, we can multiply this out. So y is equals to, let's multiply this out then, we got 2x squared plus 2x plus 3x plus 3. And that gives you 2x squared plus 5x plus 3. So a little bit of algebra. And now we can differentiate because we have separate terms. Okay, so dy dx is equals to, bring the power down, 4x to the power 1 plus, remember if you've just got a number times x, you end up with just the number. And derivative of a constant is equals to 0. Okay, so there's the first derivative of this. And of course, if you wanted to find the second derivative, then, for example, you would differentiate this. So just for a bit of practice, let's find the second derivative. So we differentiate 4x. Remember, it's a number times x, so you just end up with the number. Differentiate a constant, we get 0. Okay, so that's the second derivative. Next example then. So remember, as I said then, what ideally you want to have when you are differentiating are separate terms, which is what we've got here. But of course, these don't look very nice. They're not just x's to the power 2 or power 3, for example. So the second thing that you always want to have when you're differentiating a function is you want to have the x that you've got to a power. Okay, you want to have x to a power. Now this is where the laws of indices come in very useful. So let's express these as x's to powers. So if you remember, square root of x is equals to x to the half. So it's up to you if you put it in decimal or fraction. I find that with differentiation and integration, it's easier to put them as decimals. You'll see in books quite often they write them as fractions. There's not too much difference. Of course, there's a little bit of difference in accuracy if you substitute numbers in then. But in terms of what we are doing here, finding first and second derivatives, it's easier if you just put them as decimals, I find. Okay, so we've got x to the 0.5. Now here, remember, we can bring this x to the 4 up to the top, and it becomes x to the minus 4. Okay, so now we've got separate terms and we've got x's to a power. It doesn't matter if they're decimals or negatives. It's done in exactly the same way. So we can find our first derivative, dy dx, bring the power down in front. So we've got 0.5x to the minus 0.5. Okay, so of course 0.5 take away 1 will give you minus 0.5. So you've got to be a bit careful with these. Here we're bringing the power down in front. Okay, so bringing the minus 4 down in front. So we've got minus 4, and you've got to be careful, of course, if there's a negative there in the first place. Minus 4 x to the power minus 5. Okay, and we've got to be careful here when we're taking 1 away from minus 4. Very common mistake, because people are so used to taking 1 away from something like this. They will write that down as x to the minus 3, because they're taking 1 away from the 4 without thinking that it's a negative. Okay, so just be careful with that. I do see that mistake sometimes. Let's try another example. So if we've got, for example, then y equals to x to the 4 plus 3x squared divided by x. Okay, so you've got to do a bit of algebra sometimes with these. So first of all, remember, if we've got multiple terms divided by one term here on the bottom, we can split that into two fractions. So we've got x to the 4 over x plus 3x squared over x. And again, a little bit of algebra then. We've got y is equals to x to the 4 divided by x is x cubed plus 3x squared over x is 3x. Okay, now we've got separate terms, so we can differentiate, and we get dy dx as 3x squared plus 3. So that's the derivative of this function here. Okay, so we'll look into a method later on when we've got more complicated functions divided, called the quotient rule. Okay, but whenever you've got x's involved, such as this, so fairly straightforward algebra, we need to try and manipulate it in order to get separate terms, and then we can differentiate it. Okay, but this could be done with the quotient rule that we'll have a look at later on. Another popular one that you will see from time to time is the derivative of ln x, okay, so log to the base e of x. And what you've got to remember with this one, and we can go straight for the derivative, there's a bit of a trick in order to differentiate logarithms. Okay, what we need to do, first of all, is we differentiate what is inside the log. Okay, so we differentiate what's inside the log. Here we've got x inside the log. Okay, so when we differentiate x, we get 1. People tend to struggle sometimes with the differentiation of x on its own. Remember I said when you've got a number times x, so 5x for example, you end up with a number in front of the x. Yes, so 5x differentiated is 5. Here of course we've got 1x. Yes, so the differentiation of 1x is just 1. Sometimes people make a mistake and say it's 0. Okay, but of course that's not correct. So anyway, back to differentiating this logarithm. So what I said then is we differentiate what's inside the log. So we're differentiating this x, which is 1, and then we put it all over whatever is inside the log. So we've got x here in the log, so we put x underneath. Okay, so this is a form actually of what we call the function of a function rule. Right, so for example, if we've got another log, so say we've got ln of 3x squared. Let's try and differentiate this. Remember what I said, we differentiate what's inside the log. So what's that going to be? 6x. And then we put it all over whatever is inside the log. That's over 3x squared. And of course, quite often with these ones, things will start to cancel because of the nature of what you're doing is you're dividing through by something. Things will start to cancel. So 3 goes into 6 twice. And we've got an x on the top and x squared on the bottom, so we can cancel one of the x's on the top with one of the x's on the bottom. So what we're left with then is just 1x on the bottom. Okay, so x goes into the top once and goes into the bottom once as well. So we've got that first derivative of ln 3x squared as 2 over x. Let's have a look at the more complicated, well, not so much complicated, but different types of standard derivatives that don't involve just basic algebra. A popular one is y equals e to the ax, okay, so the exponential function. Here, ax, where a is any number, okay, so this could be, for example, e to the 4x, something like that. So the standard derivative for this, so dy dx for this is equals to a e to the ax, okay, a e to the ax. So in other words, you're bringing that a down in front of the exponential. Okay, so for example, if we do a quick one, e to the 4x, this will be, if we differentiate this, 4e to the 4x. Okay, 4e to the 4x. But can you see what we're actually doing here? We're actually differentiating this power and bringing it down to the front. Okay, we're differentiating this power and bringing it down to the front. 4x differentiated is 4. Yes, and then we're bringing it down in front of the exponential. So that's quite an important tip for example, if you're differentiating something like e to the sine x. Okay, we would differentiate sine x and put it in front of the exponential. And as we're talking about trigonometric functions then, such as sine x, let's have a look at how we differentiate these. Okay, so the ones we look at are sine ax, where a is any number. Okay, so if we've got y is equals to sine ax, then dy dx will be equals to whatever I write down on this side. cos ax, and of course tan ax as well. So when we differentiate sine ax, we get a cos ax, okay, a cos ax. When we differentiate cos ax, we get minus a sine ax. And when we differentiate tan ax, we get a sec squared ax. Okay, sec squared ax. So you might remember, if you've looked over the trigonometric equations lecture, that sec squared x is the same as 1 over cos squared x. Okay, and there's a way of proving that actually by using the quotient rule. Okay, so they're fairly straightforward, but you've got to be careful, particularly with the negatives. Okay, and when we get on to integration, you'll see that these are very similar to the integrals, so you do have to be careful with them. So for a quick example then, if we did the derivative of, say, sine 5x, we would get 5 cos 5x. Okay, so it's in this form here. Got to be careful if we start to involve fractions. So for example, if we did cos of x over 5, okay, derivative of cos x over 5, of course this can be written, if we want to write it in the form that I just rubbed off the board a second ago, we could write this down as cos of a fifth x. Yes, so a fifth x is the same as x over 5. And now we can differentiate using that standard derivative. Okay, so dy dx is equals to minus a fifth sine x over 5, or you could write it as a fifth x, of course. Okay, so this is how we differentiate the trigonometric functions. Very, very important when we get on to the product rule and quotient rule and chain rule later on. And of course, as long as these terms are separate, we can differentiate them separately. Okay, so in this case, for example, if we wanted to differentiate, so dy dx, if we wanted to differentiate this function, so we've got 2 multiplied by the derivative of sine x. So of course the number in front of the x here now is 1. So when we differentiate sine x, we just get cos x. Yes? So if you wanted to use the standard derivative that I wrote down a second ago, that would be 1 cos 1x. But of course you don't tend to write the ones in when you've got them in front of algebra. Okay, but of course it's multiplied by 2. So what we've got is 2 cos x. Slightly trickier one here now. We've got minus 3 cos 2x. So I'm going to do this in stages just to show us what's happening. We've got minus 3 multiplied now by the derivative of cos 2x. Now, of course, the derivative of cos 2x is minus 2 sine 2x. Yes, so using that standard derivative from a second ago, it's minus 2 sine 2x. And of course, now we can simplify this. If we multiply these two together, minus 3 times minus 2, of course, is a positive 6 sine 2x. So this is the first derivative of that function. So you've got to be very careful when you're differentiating cosines, particularly when you've got negatives in front of them already. Okay, but when we've got numbers in front of sines or cosines or exponentials, they work in exactly the same way as when you've got numbers in front of just something like an x squared, for example. Okay, so it's always that number multiplied by the derivative of the function that we're differentiating.